Welcome back, Pre-Calc friends, and today we're going to talk a little bit more about section 3.2. In the beginning of 3.2, what you already learned was the idea of logarithms, what they are, how we can play with them. We looked a little bit how we can switch back and forth between logarithmic and exponential form and how useful that was. And then just plugging logarithms into the calculator and doing that. Here today, we're going to sort of mirror what we did in 3.1. In 3.1, we talked about the graphs of exponential functions, how they were growths or decays, but we talked about the fact that we're not going to really graph them by hand anymore. We're just going to talk about transformations and can we identify them. Here, same idea. Let me just talk about log graphs with you, what they look like, but we're not going to have to graph them by hand. We're just going to talk about basically what the transformations look like. Well, the log graph, because logarithms in general, we learn them as being the way of undoing an exponential. Do you believe that the logarithm basically is the inverse or undoing of the exponential function? So if we can just take our exponential function or graph and just switch x's and y's, we've got our logarithm. That's pretty cool. So I'm going to go back to something like y equals, how about 2 to the x? And we graph that. We learned that that was a growth function. And then we graphed this one. We had 1/2 to the x. Because that base was a small number, that exponential function was a decay function. The first one was a growth function, looked a little bit like this. And the second one was a decay function, looked like this. So our log graphs should look a little bit like the flip or the symmetry across the diagonal line for these. Let's see what that looks like. Okay, if you remember on the y equals 2 to the x graph, I'll just put the points there. We had the following points from 3.1. We had, when x was 2, we had 4. When x was 1, we had 2. And so on and so on. And so our graph kind of looked like this. That was 2 to the x. That was a base of 2, which is a big positive number, so here's a growth. Okay, now why don't we take the inverse of that, or the log of that, and what that would look like would be this. Y equals, you see how the base here is 2? This would be log base 2 of x. Log base 2 of x and 2 to the x are basically inverses of each other. So what I'm going to do is I'm going to take those points that I did on the brown graph, and I'm going to switch x and y and get my red graph. So I started with 2, 4, right? So that's going to be 4, 2 is my flipped point. I had 1, 2, goes to 2, 1. I had 0, 1, which is 1, 0, and so on and so on. As I do it, I get closer and closer, not to the x-axis anymore, but the y-axis. All right, look at this graph, friends. It looks a little bit like this. He's going to snuggle the y-axis as he gets closer and closer, and he's just going to grow very gradually to the right as I go on towards infinity. That, friends, that is in general what the shape of a typical log graph, where your b base is bigger than 1. Here in this one, b was equal to 2. My base was 2. We don't really call it growth or decay here. That's only for exponential graphs. But this is sort of the mirror or inverse image of the growth function that we had over here. Okay, so that's what that looks like. How about a typical decay function? What does that look like when I change it to a log? Okay, well, let me put the points here on this graph. This was, we had now 2, 1/4. We had 1, 1/2, 0, 1, and then it just kind of went backwards this way. When I graphed it, it started really high and then it snuggled all the way down and really got close to the x-axis as I went on towards infinity. Okay, great. So let me take those points that I just put on the brown graph and I'll flip x and y, do the inverse, and I'll get the log graph. But what's the equation going to be, friends? Can you see the base here? This is going to be log base of 1/2, little tiny subscript there, of x. All right, let's see. All right, I'm going to work left to right now. I had -2, 4, so that's going to be 4, -2. It's going to be right in the middle of my words here. That's okay. -1, 2 becomes 2, -1. 0, 1 becomes 1, 0, and so on and so forth. And now, just like on the graph on the left, I do snuggle the y-axis. But as I go towards the right, it kind of starts sinking more and more. So it kind of has this kind of interesting shape just like this. This is, folks, a log graph where my base is small, somewhere between 0 and 1. We don't see this shape too much on the right-hand side. When we talk about log graphs and log shapes, we'll generally look at the one on the left side because they come from exponential graphs that were growth graphs, and those are a little bit more popular. But I just want you to be familiar with both types. But also important to remember that the way we got these, just like we did way back in chapter 1, was by switching the x and y values. Okay, but like we said, we're not going to graph these by hand, folks. I just want to know what are the changes. So for number 1, if I give you a typical log graph, that's log base 2 of x. That's my original function. Or on number 2, if I give you log base 4 of x. Can you see in each one what are the changes? And is it an up, down, left, right movement? Is it a reflection, stretch, or shrink? Okay, well look at number 1, and do you notice here the one difference there is that 3. Do you notice that he's inside with the x? He's inside, which means he's either moving to the left or to the right because it's an addition subtraction. Remember, we always do the opposite. He looks like he's going to the left, but he's actually going to the right. So for number 1, the transformation is, this is a typical log graph that's going to the right 3. All right, how about number 2? All right, if this was my original log base 4 of x, look what I have. I have this thing, a negative sign. Remember what that does. And I have a plus 1, but he's not really with the x. Like, I know he's next to the x. Can you see he's like literally plus 1 is next to the x? But can you kind of train your eyes back here to number 1? Do you see how the 3 was inside parentheses with the x? That was definitely an x change. So I'm thinking that this plus 1 change over here is probably going to be with the y, not inside with the x. Well, the negative on the outside, that's a type of reflection, right? Because we're multiplying by a negative. But I have to think for a second which axis. And then this y change over here, the plus 1, that's a plus, so it's going to be like an up or down version. So we got to figure that out. Okay, let's talk about that negative sign. So he's a reflection, but he's on the outside. He's not inside with the x. He's on the outside, which means he's multiplying the y's. So he is a x-axis reflection. Okay, got that. Multiplying the y's by negative 1. So he's an x-axis reflection. And then over here with the plus 1 on the outside, if it's a y change, remember how we like the y changes because it's exactly what it looks like. It looks like it's going plus 1. That means it's going up 1. And it is. So there you go. So we don't have to graph these by hand, thank goodness, but just be able to identify what the different transformations are. Now, as we do transform them, it's going to change our domain. If you go back over here to the graphs, over here on the left graph, if I say, hey, what's the domain of this left graph, the one in red? Well, let's see. It looks like the red graph sort of stops around here and goes forever to the right. But it doesn't ever touch 0. So I would say the domain of this left graph would be from 0 to infinity. But it doesn't touch 0, so I'll put 0 in parentheses. And then infinity is always in parentheses. Okay. What if I go over here on the right graph? Same idea. I don't feel like he passes 0. He doesn't ever go anywhere to the left of 0. So again, the domain would be 0 to infin. Oh, okay. That's really easy. But the problem is, on number 1 here, what if I shifted my graph? How does that change my domain? And over here, number 2, did I shift my graph? Yeah, but only along the y's. So is that going to change my domain? Okay, let's figure that out. So our next goal is, can you figure out what's the domain of a shifted log graph? Now remember before what we said, when we were first learning logs, we learned that you can take the log of 10 or the log base 2 of 8. But remember the 2 problems that came up that were like, nope, you can't do that. We can't take the log of 0, right? We can't take the log of a 0. It's just not possible. We also couldn't take the log of, do you remember? Yeah, a negative number. That's just not possible. So just know that we cannot take the log of 0 or negative. It has to be positive. Okay, so when we approach these, friends, here's what we're going to do. This is very much related to the domain questions from section 1.1. Oh, yay! Let's find the domain. You can see this is a shifted log graph. I'm taking the log of x minus 4. This is inside the logarithm. Well, that number cannot be negative and it can't be 0, which means that number inside x minus 4 has to be positive. Remember we did greater than or equal to 0? But wait, didn't you just say it can't be 0? You're right. So that means what we're going to do is say it's not that it's greater than or equal to 0. We're going to literally say only greater than 0. So rip it out. Set the log expression, the log inside expression, just strictly greater than 0 and solve. That's all we have to really do. It's actually really not a hard kind of question. So I'm going to take the x minus 4. This is the thing that was inside the log. Rip it out and set it greater than 0. Because I can't take the log of a negative or 0, so I just take the log of positives. Solve, please. And guess what, friends? There's my domain right there. Look how easy that was. Just rip out the expression inside the logarithm, set it greater than 0, and solve. You want to try number 2 really quick on your own? Pause the video and see how you do. All right, friends, for number 2, let's go right to the part inside the logarithm. And it's right here. It's not the b. And notice that b doesn't really matter. I'm not really paying attention to that. It's actually just a letter here. But I don't care. All I care about is what's inside the logarithm, because that has to be greater than 0. So we're going to set 5 minus 2x greater than 0, and we'll solve. Okay, be careful of your algebra here. I have a feeling that something kind of weird is going to happen. I subtracted 5. I'm going to divide by negative 2. Okay. That goes bye-bye, and I get x is, ooh, wait. Do you see what happened? I divided by negative. Remember we said in algebra, whenever you divide or multiply by negative, you do flip the sign. And so that becomes a less than. Negative 5 over negative 2 is just positive 5 over 2. And friends, that's my domain. You know what, just for the heck of it, can we just see if this is right? Let's just double check. Can you guys pick a number that's not in that range? Can you pick a number that's maybe greater than 5 over 2, greater than 2.5? How about 3? Let's pretend that x equals 3. Can we actually plug that here into my log? Is it going to be legal? Let's see. I would get 5 minus 2 times 3. That's 5 minus 2 times 3 is 6. That's negative 1. Wait, that means you're taking the log of negative 1? No way, Jose. You can't take the log of a negative, right? So our answer must be right, because we picked a number that was wrong, and we proved it was wrong, so our domain is good. Okay, now let's use this one more time. Let's use logs. We've used logs already for, let's see, for tornadoes. We've done it for determining blood cholesterol and heart disease. There's yet another natural disaster that we can use, earthquakes, that uses logs. This is a great real-life application because it uses something very familiar. Have you folks heard of this? This is what they usually use to measure the magnitude of an earthquake. When an earthquake happens, and you hear on the news that it's a 5.4 magnitude earthquake, they use that by using a Richter scale. Now, here's the equation of a Richter scale. Did you ever know this? I didn't. But look what I see right away. Look what's inside the Richter scale equation. A log. Yay! So that's a great use of logs in real life. So here's what the magnitude of an earthquake would be. The magnitude of the earthquake is 2/3 times the log of this crazy expression, where E, as you see here described on the bottom, E is the energy that was released by the earthquake. When the earth shakes like that during an earthquake, it releases a massive amount of energy, usually in terms of joules, if you've heard of that before in science class. So it releases a massive amount of energy. We take that and we divide by the baseline number of 10 raised to the 4.4. Why? Just part of the formula. And then we take the log of that expression. Can you see what the base is of my log here? Do you see how there's nothing there? So what's the base? It is 10. That's great. Why is that great? Because that's the common log that we use on our calculator. Great. So we can use this very easy by punching this log into the calculator. All right, so there's our formula. You don't ever have to memorize it. I will always give it to you. You just need to know how to apply it. Okay, ready? Let's actually try this one. One of the most popular places that they have earthquakes is California. So let's go find an earthquake in California. Okay. Way back in 1989, October 17th, there was a massive earthquake in San Francisco. I remember that day well because I was there. I think the earthquake was a Tuesday, and I was there on Sunday, and I left just in time. But I remember this was on a Tuesday, 1989. It hit San Francisco right in the middle of the World Series, and we want to find out what's the magnitude. The earthquake was pretty strong, and it released this much energy. So that is your E value. So can we find the magnitude of that earthquake from October of 1989? 31 years ago. All right, let's use our equation up here, friends. M equals, the formula is 2/3 the common log, base 10, of E. Now the releasing energy was 1.12 times 10 to the 15 power. That's E. And then the formula says divide that by 10 to the 4.4. Great. Okay, so how do we put this in the calculator? Oh my gosh. Well, it's a bit complicated because of this scientific notation right here. So it might be easy just to do that in your first step. Go ahead and just in your calculator, can you do 1.12 times 10 to the 15? Or if you know your scientific notation, you just know that that is 15 zeros to the right. So I can just do 1, 2, 3, 4, and keep going all the way, and just type that number in. Or, like I said in step 1, just write that into the calculator. I'll do 1.12 times 10 raised to the 15th power. Okay. And I'm going to get a huge number. And it is basically 1.12 with a ton of zeros after it. Step 2, after you do that, can we divide by 10 to the 4.4? So I'm going to do divide by 10 to the 4.4. And I get somewhere about, this looks like maybe about 44.5 billion. All right, that's a massive number. But then step 3, using your answer button, can you just do the log of that number? And I take the log base 10 of that number, I get about 10.6 or so. So far I've got 1, 2, 3 done. And the last step is go ahead and just multiply your answer by 2/3. So I'll do multiply by 2 and divide by 3. And I get, usually who you see magnitudes in terms of one decimal place, that was a 4.2, a 10.9, or whatever. This is 7.099, so I'm going to round it to a 7.1 magnitude earthquake, which is pretty darn big. And it was a long time ago before the buildings were retrofitted for earthquakes, so there's a lot of damage that happened. Okay, so again, there's a great application for logs, is determining the magnitude of an earthquake using the Richter scale. This is base 10, so we can put it in the calculator. E is the energy that the earthquake releases, and it's just now plugging it in to the calculator. Try to figure out that first E number using your calculator. Divide it by 10 to the 4.4. Take the log of your answer, base 10, and then multiply by 2/3, and you've got the magnitude. How cool is that? So that's the end of section 3.2, friends. Good job today. See you next time.